Okay, in this example, you are required to find the force in member CF and decide whether it is in tension or compression. So, you nampak je dia minta member CF. Does it mean you need to cut off or section off only the CF member? No, no, no. Jangan buat kerja gila macam tu. When you want to apply the method of section, you have to section it out from the top to the bottom. Meaning dari atas truss structure tu sampai ke bawah, the entire structure, okay? Okay, just like the previous example, before we proceed with the method of section, we have to identify first the support reaction magnitudes happening at each joint, okay? So at joint A, there's a pin over here, and there should be two forces acting in the Y direction and also in the X direction, okay? Whereas at joint E is a rocker type of joint, so there should be one force in the Y direction. When you have identified the direction of the support reaction at each joint, the next step is to apply the equilibrium condition so that you can find the magnitude of respective support reaction. Okay, I'm going to fast forward this particular part. You should do it on your own because you should be very familiar with this step. If we apply the equilibrium condition in the X direction, you will get the magnitude of AX to be 0. Similar like the previous example, we can't apply the equilibrium condition in Y direction because there are two unknowns, AY and EY, so it doesn't solve our problem. So probably I am going to proceed the equilibrium condition for moment, and this time around I'm going to apply the moment at point A. Why point A? Because there are many forces happening at joint A, so I just want to cancel out that external forces, so that's why I apply the moment at point A. Okay, recall the formula for moment is equivalent to F multiplied with the perpendicular distance. Okay, I'm going to fast forward this particular part. You should be very familiar with it again. So at the end of the day, you will get only one unknown variable in the equation, which is EY. So you can easily solve for EY and you will get the magnitude of EY to be 4.75 kilonewton and the direction is upward. Okay, finally, you can apply the equilibrium condition in the Y direction pula, okay? So, if you put up all the forces acting in the Y direction, there will be only one unknown variables left, which is AY. So, you can easily solve for AY and you will get the value of AY to be 3.25 kilonewton and the direction of AY is upward. Okay, now that we have all the magnitudes of the support reaction forces, the next step is for us to apply the method of section. Okay, so if we apply the method of section, we have the choice either we want to solve this problem from the left side of the truss structure or from the right side of the truss structure. Okay, accordingly, let me check. Okay, how many external forces are there if we are to solve it from the left side of the structure? There will be only two external forces, which is AY and also the 5 kilonewton. And if I were to solve it from the right side of the truss structure, again there will be two forces as well, which is 3 kilonewton and the EY. So in this case, you can choose either the left side or the right side to proceed with your analysis, okay? So I would choose the right side because it have a lower number of truss members, so it will be easier for me to redraw the truss diagram. Okay, now let me just quickly redraw the section on the right. Okay, so these are the joints and these are the truss members. So the next step is we draw the support reaction forces at joint E, which is 4.75 kilonewton, at joint D, which is 3 kilonewton, and finally let us redraw the internal forces at each truss member. Okay, so we know that is an internal force between joint C and D, so we are going to call it FCD, and then there is an internal force at BMCF, we are going to call it FCF, and finally there are another internal force at member GF and we are going to call it FGF. Okay, as there are multiple sengat-bengat punya forces in this particular section, so we have to find what is the angular displacement between the members so that we can resolve the sengat-bengat punya forces into an equivalent X and Y direction, okay? So if I were to sketch the triangle at this particular area, and I'm going to call this angle to be theta 1, we know the distance over here is 4 meter and the distance over here is also 4 meter. So So you know that this triangle adalah triangle kaki sama. So kalau triangle kaki sama, it means that the angle theta 1 here would be 45 degree. Okay, sebab dia punya kaki tu sama, 4 meter and 4 meter. So the 45 degree would be over here. So if you resolve the FCF into the x direction, you will get the FCF to be FCF cos 45. And if you resolve it into y direction, it will become FCF sin 45. Okay, now let us find another angular information so that we can resolve the FGF into an equivalent x and y direction. Okay, so now looking back at the original diagram, let me draw the triangle at this particular section. So the distance over here will be 2 meter and the distance over here will be 4 meter. And using the trigonometric formula, you will get the hypotenuse distance to be sec 20. Okay, so if I were to redraw this triangle over here, this would be my theta, this is 2, this is 4 and sec 20 will be over here. Macam mana dapat sec 20? Okay, ingat the formula of triangle. Kalau nak dapatkan the length of the hypotenuse, it will be 4 squared plus 2 squared punca kuasa, and you will get square root 20 or sec 20. Okay, now back to our truss section. So now we can resolve FGF into an equivalent x direction. And the magnitude will be FGF sin theta. So if we take the theta over there, so sin theta will be tentangan, which is 4, over hypotenuse, which is 20. Okay, accordingly, if you resolve the FGF into a y direction, it will become FGF cos theta, whereby based on this triangle, cos theta would be 2 over 20. Okay, now we have resolved all the sengat-bengat forces into an equivalent x and y direction. Then only we can solve for all the internal forces, whereby we need to find the magnitude of FGF, FCF and also FCD. So if we apply equilibrium condition, it's up to you whether you want to apply from x, y, z, or if you want to apply at moment direction. So I think for the first part of equilibrium, I'm going to apply the equilibrium condition for moment at point F. Why point F? Because there are many sengat-bengat forces passes through point F. Okay, so if I apply moment at point F, I can actually cancel out that sengat-bengat punya force, and I can focus on only the linear XY punya forces. Okay, if I want to calculate the moment produced by this force, so this FGF, it passes through the rotation point F. So there are no moment produced by this force. So we can ignore the calculation of moment over here. Accordingly, FCF also passes through rotation point F. So we can also ignore this particular force as it will not create any moment about point F. Okay, how about this force, FCD? Okay, of course, there are moments produced by FCD. So, the magnitude of force is FCD unknown, and the perpendicular distance from the line of force to the rotation point F will be 4 meter. If you draw an imaginary circle around rotation point F, you will get the direction of FCD to be clockwise direction. So, it become negative. Okay, try to complete the remaining moment equation on your own, and there will be only one variable left, which is FCD. So you can simply solve for FCD to be 4.75 kilonewton, and the direction is to the left. Okay, now I'm going to apply the equilibrium condition in the x direction. You try to do this on your own, and at the end of the day, the final equation will become like this. You cannot solve it just yet because there are two variables or two unknowns in your equation, which is FGF and also FCF. So we'll just leave it as it is, and we'll call this equation to be equation 1. Now let us proceed the calculation by applying the equilibrium condition in the y direction pula. Okay, again I'm going to fast forward this part. You try to do this on your own, and at the end of the day, your final equation would look something like this. Again, similarly, you can't solve it just yet because there are two variables or two unknowns, which is the FGF and also the FCF. So we are going to call this equation equation 2. Okay, if you look carefully, equation 1 and equation 2 are simultaneous equation. So you can easily solve these two simultaneous equation using the calculator. So your A1 would be 4 over sec 20, your B1 would be cos 45, and your C1 would be 4.75 kilonewton. On the other hand, your A2 would be negative 2 over sec 20, your B2 would be sin 45, and your C2 will be negative 1.75. So you will get the magnitude of FGF to be 4.8448 kilonewton and the magnitude of FCF to be 0.5893 kilonewton. Okay, if I were to redraw the member of CF like this, and I'm going to resketch it over here, the direction of the FCF is positive, so it means that our initial assumption is correct. So FCF at one end is in this direction, and then at the other end would be in the opposite direction. So notice that the couple force are creating a compression kind of force onto the member CF. So therefore, member CF is in a compression state. Accordingly, I forgot to sketch the diagram for the member GF, so you can try to do this on your own. Similarly, you will get the member GF to also be in a compression state. Okay, dah siap. So, I'll see you in the next lecture series.